Hey, in this video, I'm going to go over a workflow for setting up USD components in SOPs. We'll be covering the fundamentals of how hierarchies can be constructed in SOPs, how to extract and set up scopes, purposes, and subcomponents, how to set pivots, dealing with nested Xforms and subcomponents, and some basic rigging and animation workflow. Now, we won't be going into class inheritance or payloads. For reference on that, take a look at the component builder workflow. Here, we're just focusing more on the nuts and bolts of building clean, useful hierarchies in SOPs. So let's get started. We'll start off in Solaris, also known as the stage or LOP context. There's a bunch of different ways of importing SOP geometry. If you want to pull geometry from the usual object context, then a scene import or a SOP import is the way to go. Here I'm going to use a SOP create because the viewport ghosting can give us a really handy visual for how our geometry is being translated to the stage. So let's dive inside and make some geometry. Just going to put down a bunch of boxes and some spheres. And we'll merge those together. Here you can see it's useful to have both your scene graph tree and geometry spreadsheet up to clearly see how your SOP geometry is translating into USD. So we have a bunch of objects merged together, but in our scene graph tree, we see that our component only has one gprim named mesh_0. Why is that? So in SOPs, we're essentially always looking at what's known as leaf primitives, meaning meshes and renderable geometry. That's at the very bottom of the hierarchy. Usually a SOP network is just a big container of primitives that we want to render. We can organize the primitives by labeling them with attributes. By default, Houdini looks for name and path. I'll use name because it plays nicely with KineFX, which will be more important later. So let's name our objects. So I'll put down a name. To make this easy, I'll just say $OS. We'll call it box01. And then we'll do box02, sphere01, and sphere02. And now you can see we have separate primitives for each mesh. Handy. But what if we want a different structure? Say we want to group these meshes under different transforms. We can do that by specifying a path rather than just a name using the / separator. So I'll group the spheres under spheres and boxes under boxes. We can do that by just using a second merge, one for our spheres, one for our boxes. We can merge these back together. So now we've got the same hierarchy we had before. So let's alter the paths. So I'll do that using a name. And what we can do is rename. So we'll clear the name, add a rename. And if we just say star, rename to boxes/star. And now we'll take this and put it here, and we'll say spheres/star. Now you can see this automatically creates new primitives here called boxes and spheres, and it by default will always set those to an Xform. Note that what we're doing here with the paths are known as relative paths. If you put a / at the start, it becomes an absolute path. That does something different. You can see it's renaming our component here. We're just going to stick with the relative paths for now for simplicity, but you can play around with that later if you want. When building components, it's useful to put all of your geometry under a geoscope and then under a separate scope for render and proxy purposes. So let's have a look at that now. Put down another name and we'll do a rename from star to geo/render/star. And we'll call this name scopes. And you can see now we have Xforms here for geo and render, and then here's our boxes and spheres. Now, if you don't understand what scopes and purposes are, we're going to go over that next. There's just one more thing I want to look at first, and that's geometry subsets. So in USD, it's preferable to keep your prim count as low as possible. And that means ideally all of your geometry should exist in a single prim where possible. The exceptions being that when you need to move pieces around independently and they need to have separate transforms, like in this case, we might need separate transforms for each of these spheres and boxes, or when you need to toggle separate visibility or subdivision for different parts of your model. Otherwise, you want to merge everything into as few a number of mesh prims as possible. But you still need to assign materials to those things, so that's where geometry subsets come in. Let's delete these. By default in the SOP create, under import from SOPs, import data, you can see partition attributes shop material path is on, and this check down here saying prefix subsets with attribute name is on. So if I come in here and add a shop material path, so you can do that with the material node, or we can do it with an add create. I'll just come in here and add one to everything. Shop material path, it's going to be a string primitive, and we'll say metal. Or maybe we want to grab just some of the mesh. So just those faces. And we'll call this paint. And now if we have a look in here, it's not a very useful visualization, is it? There we go. Now we see we've got different materials assigned to each piece. And in here, you can see now we've got this extra drop down that says shop material path metal, shop material path paint. And so we could then assign materials to these different parts of the mesh. I don't like that it adds this prefix. So we can change this either on the SOP create by unchecking this. Now it's gone. Or if you're working in SOPs directly, we can put down a USD configure and we get all these same settings. And you can go to import data, set your partition attributes, turn off this prefix. You can alternatively create geometry subsets with groups rather than attributes. There we go. So now that we have our leaf primitives all set up, we need to configure the other prims in our hierarchy, such as render and geo here. This is done in SOPs using points with various attributes that Houdini looks for. Let's take a look at a simple example. Materials and components are usually housed in a scope called MTL. Since we won't have any leaf primitives under it, we can't add it automatically by naming parts of our mesh like we did with the geo and render Xforms earlier. We'll need to add it manually. So here's how that's done. At the end of our network, we'll merge in another branch of geometry containing only points. We'll put down an add node with one point to start with. Now let's name that point MTL. Note that you'll need to set the name attribute to points rather than primitives now. You can see in the scene graph tree, now we have a points prim named MTL. We can set the primitive type we want by setting the USD prim type attribute to scope. This will be a string attribute, scope, note the capital S. Now you can see the icon's changed, and that's turned into a scope. A scope in USD is kind of like a null object with no transform. It's a way of organizing your hierarchy by grouping together primitives, but without introducing unwanted transforms. Let's do this for our geo and render scopes as well, and we'll also add a proxy scope. More on that in a moment. Change this to $OS to make it easier. Let me just copy these across. Call this geo render proxy. And now for these two, we need to say geo slash and geo slash. Now let's merge all these together. You can do this inline or just add more points in here, but I find it easier to illustrate things laid out this way. So now you can see our geo is turned into a scope, and we've got a proxy scope here and a render scope here. Our geo underneath. So now that we have our scopes set up, let's have a look at purpose. USD purpose allows us to have a separate lightweight proxy geometry to work with in the viewport and then let the renderer handle the denser full quality mesh at render time. To do this, we need to set the USD purpose attribute on our scope points, render for render, proxy for proxy. We do that in the same way with an attribute create. Call this render purpose, and we'll say USD purpose. Let's say string, and we'll say render. And then for proxy, we'll say proxy purpose. And we'll set it to proxy. Now if we come into here and add purpose to this list, we can see now we're setting proxy and render. Now if we jump back up to the stage, we might need to just kick this a bit. Sometimes the viewport gets a bit stuck and you use toggle nodes on and off or toggle some settings. But you can see that our mesh looks like it's disappeared. This is because if we have a look in the scene graph tree, we don't have any meshes under proxy. And if we look at the little sunglasses icon here, you can see that we're only looking at proxy, we're not looking at render. If we turn render back on, our geometry comes back, turn it off, it's gone. So in order to see our mesh, we need to add our proxy mesh. So let's do that now. Since our geometry is really basic, I'll subdivide everything to artificially increase its poly count. There we go. Then to set up the proxy mesh, add a name SOP, set to rename, and all we really need to do, take this render part of the name path and swap it out for proxy. And then everything in this branch will appear under the proxy scope. So let's do that here. We'll say star render star, and we'll replace it with star proxy star. And you can see now everything is grouped under proxy. And if we merge that back in, we now have our render geometry and our proxy geometry. This isn't very useful as we've effectively just duplicated the mesh. So we'll put down a poly reduce to cull the mesh down to a more lightweight representation of our render geometry. Now if we jump back up to stage, turn on wireframes and see there's our proxy geometry and there's our render geometry. Grabbing the selection tool, we can see that there are options for easily selecting leaf nodes, Xforms, and subcomponents. While any Xform can be moved around inside of your components, if there are pieces of your component that are specifically designed to be animated, it's preferable to set the kind of that Xform to subcomponent. Kind is basically a USD label for grouping renderable parts of your scene. I won't go too deeply into kind here, but for our purposes, all you need to know is that component is a kind, and any moving parts inside of a component should be a subcomponent kind. Let's jump back into our subcreate and set that up. Let's say we want to turn our spheres and boxes Xforms into subcomponents. We'll need to do a bit of rearranging of the hierarchy first, because at the moment we have a single geoscope with separate Xforms for spheres and boxes in both render and proxy. We want to reverse this so that we have only two Xforms at the top, one each for boxes and spheres, and then each of those will have their own scopes underneath. We'll do this by tweaking the paths in our name attributes. So we'll bypass this merge for now. So we're just looking at our mesh hierarchy, and we'll delete this name scopes, and we'll set our scopes individually on here. So here we've got boxes / star, the star being the name of each box, and we'll change that to boxes / geo / render / star, and we'll do the same here, spheres / geo / render. And now this is the hierarchy we want. We've got our boxes Xform with geo, proxy, and render under that, and spheres with geo, proxy, and render under that. So now that we've reorganized our mesh, we need to do the same to our point-based hierarchy. Easy way to do that is come in here, do a rename from star to boxes / star. And we'll create a copy of that, merge it in together, and we'll call this one spheres / star. Now if we come back down here, what have we done wrong? These name nodes are set to primitive. We're going to set them to point, and there we go. We've got our scopes under each subcomponent, under each Xform. We need to turn them into subcomponents. To do that, we need to add 2 more points to our hierarchy. Put down a merge. We'll move these over. So these are all of our scopes, and now we want some Xforms. So we can just grab these, and we'll do one for boxes, one for spheres, merge them together, and merge them in. Now you can see in our hierarchy here, it's overridden our Xforms with points. So as before, let's just grab this set scope. We're going to say set subcomponents. Now the type of the subcomponent is going to be an Xform. So we'll set the USD prim type to Xform, capital X. You can see now it's gone back to an Xform. And we're also going to set our USD kind to subcomponent. Now you can see those Xforms have turned into subcomponents. And each of those has their own proxy and render geometry inside. You can also see in the kind column here, it says subcomponent. Jumping back up to the stage, we can now set our selection to subcomponents. We can easily grab these subcomponents and move them around and animate them how we like. Something that you'll notice in Solaris's edit lot is that when you select a prim, the pivot will be the centroid. If you want to see the actual pivot, you can right-click and change it to transform. I'm on 19.5.569, and there seems to be a bug where you need to toggle centroid and transform back to get things to work properly the first time. Hopefully in future versions that bug will be gone. Doing this, we can see that our subcomponents pivots are at the origin. This makes sense, as if we jump into our SOP create and look at our subcomponent points, we can see that they're both sitting at the origin. Something to note for modeling for USD is that the recommended method for setting pivots in USD is to have your meshes at 0 and then move and rotate them into position. This is different from the usual 3D workflow of setting explicit pivot translations and rotations. Here's where KineFX comes in. We'll put down a rig pose and set our pivots. Using a rig pose node lets us move as well as rotate and scale our points by altering the P and transform attributes. You can see it's useful to set our rig pose here with our subcomponents rather than on the whole hierarchy, because there's a lot of scopes here that don't have Xforms, so they can't move. So we'll grab our spheres and we'll put them here, oriented towards the other sphere. We'll grab our boxes and we'll stick it there. Now, as you can see, we're getting a double transform. This is because in SOPs, everything is in world space, but LOPS is expecting local space. Again, KineFX to the rescue. After our rig pose node, we'll name that set pivots, put down a compute transform. This sets an attribute called local transform on our points. This is a 4x4 matrix that describes the position, rotation, and scale of those points based on what that rig pose node has done. What we then need to do is apply the inverse of that transform to our mesh. So first, we need to actually copy this attribute over to the points on our mesh. The easiest way to do this is using an attribute copy. Call this copy local transform. And we want to copy local transform. Now, in order to tell the attribute copy which points correspond to which subcomponent point, we need a matching name point attribute on our mesh. To do this, we'll promote our name primitive attribute to points. We'll say name to points, primitive to point, name, and we want to make sure to turn off delete original, otherwise we'll lose our hierarchy. So now we've got a name attribute on our points and our primitives. So the primitive name attribute is still going to be driving our hierarchy, and the point name attribute is going to be used to match up the subcomponent to the points on our mesh. Now at the moment you can see that this doesn't match, so we've got our full path, and we just want the subcomponent name. Now, because we're using a flat hierarchy, this is nice and simple. It's either going to be boxes slash, or it's going to be spheres slash. So we can use a name SOP to rename that point attribute to match the subcomponent. So we'll say from boxes slash star, boxes star to boxes, and from spheres star to spheres. Now you can see our name either is boxes or spheres, and that corresponds to our subcomponent here. So on the attribute copy, we'll say match by attribute, name. So now that our mesh has the local transform attribute, we can apply it using a transform by attribute SOP. We'll call this inverse local transform. Set this to local transform, and we want to invert the transform. The benefit of this node is that it also transforms attributes on your points. So things like normals, velocities, and matrices will also be transformed as well as just the points. Now if we go back to our endpoint here, you can see that the meshes in the viewport still aren't lining up, but that's actually what we want. Our meshes in SOPs have been transformed to their local space, and then the transforms from our hierarchy points are being correctly applied in LOPs. To confirm this, we can jump back up to the stage. As you can see, the pivots are now in the right position and orientation. We can even go a step further by reposing our mesh in SOPs. Let's jump back in, and we'll put down another repose. We'll call this repose, and we can transform the points in here. This means that for assets with rigidly transforming subcomponents, you could have your component definition and KineFX rig all in the one SOP node. That's probably not a good idea, and later we'll look at a better way of doing this, but it's good to know what's possible. Let's take a look at a more complicated example using nested subcomponents. I have this robot arm for a turbo squid that I've prepped. I just cleaned it up a bit, got it into the right scale, and named the various parts. Now these parts obviously require nested transforms, so the hand here moves when the upper arm does, etc. This adds a bit of complexity in terms of both the naming and transforms, as we'll see in a bit. As before, we'll start with our mesh. First we need to set the paths in our name attribute so that everything nests correctly. We'll do this again with a name SOP set to rename. And here we have upper arm nested on the base rotate, forearm under upper arm, and under forearm. Now we need to put our meshes under their scopes. With our simple flat hierarchy, we could use name SOPs to quickly and easily manipulate our name attributes, but this becomes more difficult when we start nesting things. So we'll need to use a little bit of ops here. Now, normally I do this sort of string manipulation in Vex, but it's simple enough to do in VOPs, and I'll do that here to avoid scaring anyone away. So we'll put down a primitive op, call it add scopes and shape, and dive in. Now what we want to do is take our name path, add our scopes to it, geo and render, and then add back on the mesh name again, which will be the last part of the path. So let's put down an add and connect our original name. Then we'll make a palm for our scopes and plug that into the second input. Next we'll need to get the mesh name. We can do that with a split with the / as a separator. This splits our path up into pieces. To get the last piece, we use a get element set to -1, meaning the last element, and plug this into the third input of the add. Now this last one is optional, but I'm going to add a suffix to the mesh names to differentiate them from component names. I'll use shape, as that's what you usually get when bringing in meshes from something like Maya. And now to update our name, let's copy this bind across, and update, and plug it in. Now if you have a look here, you can see our names are just repeating the last element. So hand is repeating hand, upper arm is repeating upper arm. That's because we haven't added anything into these parameters yet. So that's not named yet, so we'll call this scopes. There we go. So for our scopes, we want /geo/render And you can see we need an extra slash on there as a separator, so we can chuck an extra slash on. And for shape, I'm just going to say shape. Now, if we have a look at our hierarchy, we can see that everything now has a geo underneath it with a render, and then we have our mesh with shape as a suffix. And that applies to all of the nested meshes as well. Next, we'll set up our proxy mesh just like before. We'll take a name SOP, rename render to proxy. There we go. Then we'll do a polyreduce and simplify the mesh before merging it back in. Perfect. Now you can see our proxy and render scopes. That's pretty much it for our geometry. One last thing I'll change is to remove the Xform for the base. This part doesn't need to move, so it can just go in the root geo scope of the component. To do this, we'll use a name SOP to simply remove base slash from the start of any name paths. There you go. Now you can see the base is just in the root geo scope, and we have a separate Xform here for base rotate. I'll just stick a null here for the output. The reason I'm using a null as an output rather than the output node is that this allows me to jump up and down the node tree and see what the output is at any point, whereas the output node, we'd have to connect it to different parts in order to see what the output is at various parts of the tree. Useful for debugging, but in production, it's usually a better idea to use the output node. Now with that done, let's build our point hierarchy. Rather than do it manually like we did in the last example, let's pull the prims that we want procedurally. So after the restructure in the name SOP, we'll promote our primitive name attribute to points and uncheck delete original attribute. Same as before, we'll use this to copy our transforms over, but unlike last time, we'll also use this to extract our point hierarchy as well. So we'll branch off and put down a pack. Set the name attribute to name, transfer the name attribute, and set the pivot location to origin. Next, put down an add SOP set to delete geometry but keep points. What we've got now is all of our subcomponent points. Actually, we have one extra, which is the base that we decided won't be a subcomponent, so we'll delete that with a blast. Now let's set our prim type and kind attributes like before, and then merge them in. Now we'll look at the scopes. We'll branch off from the add node where we had all of the subcomponents plus the base. Here we want to add our scopes. So to do that, we'll use a name SOP again and append our geo and render scopes. Make sure to set the name SOP to point. And there we go. And just like before, we've got that extra base Xform in here. So we can get rid of that by just copying this name SOP over and setting it to point. Now that's gone. So what we have here is all of our render scopes. Now we need to get our geo and proxy scopes as well. So on one branch, we'll use another name SOP to remove slash render from our paths. That'll give us our geo scope. And we'll copy this across. And on this branch, we'll replace render with proxy. Now once we merge them all together, we can set the prim type attribute to scope. And then on our render and proxy branches, we can set the appropriate purposes. And merge it back in. And done. That's our whole hierarchy set up. Now let's set our pivots. I'm going to go to the side view and set all my pivots and orient them so that we have the Z axis aiming down the joint. As before, we'll compute the transform. copy the local transform matrix to the points, and then transform by attribute set to invert. Okay, let's go back up to stage. There are two problems here. Let's start with the obvious one. Our mesh is gone. Closer inspection will reveal that it's just the proxy mesh that's gone, not the render mesh. What's happened is the polyreduce node has cleared our name attribute, so the attribute copy couldn't locate the proxy mesh and therefore filled it with null matrices. This in effect scales all of the mesh down to 0. To avoid this, we'll just go into our polyreduce, and right down at the bottom under make reduction sensitive to attributes, we'll add name. And that brings our proxy mesh back. Cool, so now we can see the second problem. Our subcomponents aren't in the right place. This is because once again the SOP points are in world space, but Solaris is expecting local space. So now that our subcomponents are nested, we need to get their local space with respect to their parent. Once again, KineFX can sort this out. After we compute the transform for the pivots, let's put down an add node and we'll call it make skeleton. We'll set it to polygons and by group. Now that we have a skeleton, we can compute the transform again to get the correct local transform matrix. So now we have a 4x4 local transform matrix. What do we do with it? We need to apply it to our points somehow. As we went over earlier, Solaris reads a combination of the vector P and the 3x3 transform attributes. So we'll need to split this 4x4 matrix into P and transform. We'll do this with a point vault. Let's hook this up first. Move these out of the way to make the network nicer. Dive inside our point vault and put down a bind to get our 4x4 local transform. Then a bind export for our 3x3 transform. Setting the transform is easy. Just plug the local transform into the transform and make sure to uncheck override with type input. This will automatically convert the 4x4 matrix to a 3x3, which is simply the orange and scale of our transform. To get the position out, we need an extract transform bob. Plug the local transform into the Xform, and then plug the trans output into P. And that's it. We've just applied the local transform to our subcomponents. The last step is to delete our skeleton with an add SOP so we don't get this unwanted curve in our scene graph. Now, one last problem that's popped up. As you can see that our base has disappeared. That's similar to the issue we had with the proxy scope before, where the local transform is zeroed out, as you can see here. That effectively is scaling it down to 0. This is because there are no transforms on this side for that base, because we don't want to transform it. So in our transform by attributes, we don't want it to apply to anything that's in this geo scope here. So to stop it from doing that, we just say in our group at name does not equal geo/star, and we'll set our group type to primitives. And now that base group isn't being affected by this, and we've got it back. And there we have it. We have all of our nested subcomponents with their correct transforms. As before, we can always put a rig pose in here to alter our transforms and repose our asset if we want before export. With all of that now set up, we can look at how to animate our asset. If we only cared about FK, we can just directly animate the subcomponents and LOPs using a transform node in local space for each subcomponent. That's a bit clunky though, so let's build a quick IK rig. To start with, we'll need a SOP modifier. This node allows us to make changes to USD geometry and transforms in SOPs. Under primitives, we'll just put kind subcomponent. That'll grab all our subcomponents, then set the pivot location to origin, as we're happy with our pivots and we don't want them being reset to their centroids. You'll notice this immediately breaks our transforms. This is what happened earlier in the SOP create. The SOP modifier is pulling all of our subcomponents into world space. So the first thing we need to do is get them back into local space again so that we're properly round tripping our transforms through SOPs and we know our output's working correctly. So let's dive inside. To start with, we don't want these packed USDs, we just want points. So let's promote our path to a point name attribute. And then with an add SOP, delete the geometry. Now you can see we're replacing our Xforms with points again, so let's set our USD prim type attribute. Now let's set up a skeleton for our joint chain. In the Add node, go to Polygons and set it to by group. And like before, we'll compute the transforms, delete our skeleton, and convert the 4x4 local matrix to a P and 3x3 transform. Remembering to uncheck override type with input to make sure that the transform is correctly converted to a 3x3 matrix. You can see now that our subcomponents are in the correct place, but their rotations have been reset. This is because we haven't accounted for their existing transforms. To get those, right at the top of our network, we'll put down a point VOP. The USD transforms are stored on a 4x4 primitive intrinsic attribute called USD local to world transform. So put down a primitive intrinsic VOP, set it to matrix 4, first input, and USD local to world transform, and plug in the prim num. Now we just need to pipe that into our handy 3x3 transform attribute with a bind export. Remember again to uncheck override with type input to make sure we're converting from a 4x4 matrix to a 3x3 matrix. And that's it. We don't need to do anything with the positional part of the USD transform because that's already been unpacked into the P attribute by Houdini. So to recap, on setup, our transforms are being pulled into world space, and then they're being converted back to local space before export. Finally, let's do some basic KineFX rigging. So like we saw in the SOP create, we can put down a rig pose and immediately have FK control. Easy. What if we want IK as well? For this robot, I'm going to drive all of the rotations from one joint. So I'll put down a delete joints and delete everything except the tip joint, which I've named hand. Then put down a rig pose and we'll name it IK. We want our base to always rotate towards the hand, so let's start with that. We'll need a rig VOP. Plug our skeleton into the first input and our IK control into the second. If you haven't used a rig VOP before, it's similar to VOPs, but instead of using a bind and a bind export to set attributes, we're going to use get point transform and set point transform to set our joint transforms. So let's do that now. We'll need a get point transform, set it to by name, first input, and put in our base rotates name. Now put down a set point transform, also by name, and also pointing to our base rotate. If we plug the get Xform into the set Xform, nothing will happen, as we're not changing anything yet. Let's duplicate the get transform and change it to the second input and point it to our tip joint. To get the base to look at the hand, we need the aptly named look at constraint. By default, this doesn't quite get us what we want. The base should only rotate on one axis. We don't want the robot tipping over. The simplest way to make that happen is to project our IK point onto the rotation plane of the base before the look at constraint. In our case, this just means setting the Y position of the IK control the same as that of the base rotate's Y position. To do that with a 4x4 matrix is pretty straightforward. The rows on the matrix correspond to X, Y, and Z axes followed by position. This means that the second element of the fourth row of our base matrix is its Y position. And if we insert that into the second element of the fourth row of our IK matrix, we'll be setting its Y position to match the base. Let's start by getting the Y position of the base rotate. If we put down a get matrix component and plug it in, this lets us get any element out of this 4x4 matrix. So that means if we take the fourth row and get the second element, we'll get our Y position. Now to set the Y position for our IK control, we need to use the corresponding set matrix component, plug in our value, plug in our matrix, and we want to set the same value. So row 4, column 2. So now this output is the IK point, but with the same Y position as our base rotate. Now if we plug that into the lookat, it looks a bit off. So first we'll just disable this, go into our lookat, update offset, done. Now if we animate the IK control, the robot rotates to match. To get the IK articulation sorted, we'll put down an IK chains node. Select our root, mid, and tip, and then set it to match by name. I don't want to animate a twist joint for this robot, so we only have one joint coming out of the IK rig pose. But the IK chains node needs it, so we'll put down a skeleton blend to get our skeleton, but with the updated hand position. We'll set it to world space, and set the blend weight to 1. Now plug that into the second input of the IK chains. Yay, we have an IK controlled robot arm. I could leave it here, but I'd like to be able to rotate the hand. Normally, we could turn on orient tip on the IK chains node, but the base rotation messes that up. Pretty simple to fix. Since the hand is always just moving around the base, which is at the origin, let's just aim our hand based on the XZ direction of its position. I'll do this with a regular point fault. First, we'll multiply the Y position by 0 to project the point onto the ground plane. Then put down an align node and plug in our flattened vector into the 2 input. Since our joints are oriented Z down the chain, we'll set the from vector to 0, 0, 1. You can see this outputs a 3x3 matrix, so we'll export that to our trusty transform attribute. You can see that's broken out transforms because we're applying that to every one of them and we only want it to happen on the hand. So to stop that from happening, on our group, we'll select our hand, and that way it's only applying to the hand. If we animate our IK control, we can see we now have a stabilized hand joint. And now that it is stabilized, we can control it with another rig pose. For simplicity, let's copy our rotation from our IK rig pose onto the rotate hand rig pose and paste relative references. And if we want to include this in a rig HDA later on, it's good practice to go to settings, rig visualizer, add a configuration, and under joint display, turn all these off. And that way they won't show up. And now in this IK, we can animate it around and we can control our rotation. And then the last thing to do is put down a skeleton blend so that we can blend between our FK and our IK. So that's all done. We now have a pathway of getting a lightweight representation of our asset into and then back out of SOPs for animation. Let me just quickly tidy this up. As a little bonus, let's just go one step further to highlight how flexible Houdini can be. Our IK control is just a point, so it can come from anywhere. In stage, let's drop down a sphere and call it IK. Then inside of our modify, let's grab it with a lop import and copy its position onto the hand joint. Now, as we're going to be controlling this point from lops, let's uncheck our IK rig pose. And there we have it, IK control in lops. Well, that's everything I wanted to cover in this video. I found this approach to be really interesting and I hadn't seen it talked about, so I wanted to share it to hopefully encourage more artists to take up using USD in their work. I tried to keep things as simple and straightforward as possible, but there are definitely some complex topics in here that have to be glossed over, or the video would be much longer than it already is. Anyway, I hope you found it useful. Cheers.